Hello everyone, welcome to this tutorial. My name is Xarray. I'm a Google Earth Engine specialist. In this tutorial, I'm gonna show you how to find the precipitation spatio-temporal patterns using PCA analysis in the Google Earth Engine platform. At the end of this tutorial, you can produce PC components that showing dominant precipitation areas or dominant spatial pattern for the precipitation and highlighting areas receiving more and less precipitation through the time. This tutorial is very helpful and showing you one of the applications of machine learning data analysis in the Earth Engine platform using Python API programming. Okay, in the first step, you need to make a new notebook in the Colab environment. Let's start with the essential libraries in the Python that is necessary to deal with satellite data through the Earth Engine. Earth Engine library first, GEE map, and Xarray library as XR, and the next or the last one is XEE. The XEE is one of the newest library that I'm addressing in most of the tutorials, allowing us to combine Google Earth Engine data collections with Xarray structure that allowing us to apply PCA on these data using ready-to-use functions available in the Python. Let's run the cell, and now we are waiting Colab making connection with the server first, and the code is running now. After a few moments, the code executed, and once you see the successful install, there is like this message, meaning that all libraries installed and imported successfully. Now, using the EE library, I'm gonna establish a connection between Colab environment and Earth Engine, my own Earth Engine account. Start with authentication and initialize. The initialize your account information. The account project ID is necessary. If you want find of yours, go to the code editor environment, upper right, click on the icon and project info. The cloud project ID is available here. That is unique for every user. Add it into the project, just like this. And the next one, or the next argument, is OPTURL. If you search about the XEE, you will find a GitHub page, this address, that's showing a detailed instruction about how to use XEE and how to bring the data with XEE structure. So now OPTURL already addressed here, just copy and paste like this. Run the cell. After a few moments, you will have a pop-up asking you permission to connect or access to your Earth Engine account. Click on the account and press on continue and continue again, like this. So, something is wrong here. Initialize is wrong. There is a typo here. Let's run again. Now you can see the problem is solved without any issue. From now on, we can use Earth Engine capabilities in the Colab environment under Python standard. So, now we need to find the region of interest. In this tutorial, same as the other tutorials, I'm gonna actually select my own country, Iran, as a region of interest or a study area. There is United Nations geospatial data that's showing the country borders and is very useful to actually identify your region of interest without drawing a polygon. So a feature collection ID is available here. So just copy and paste it. For example, the SHP now we have countries SHP. I'm gonna select the first one to see what kind of information available in the SHP properties. Through the properties, we want to find a column or a part of information that's allowing us to filter the countries based on their name. So, as you can see, a polygon selected here. After a few moments, you can see the properties here. To get more information about the properties, you can see there is a column as name EN, expressing the name of the countries and the polygons. Okay, I'm gonna find that polygon in which the name is Iran. So let's copy the property first and make a filter. So dot filter earth engine dot filter dot string contains. I'm gonna actually find a field in the name fields. I'm gonna find those record or that record including a string contains Iran like this. So let's turn it into the ROI, region of interest. Let's run it again. As you can see, one element selected. So we have a feature here in the properties, the country name mentioned Iran. Okay, in the next step, I'm gonna do the visualization for the region of interest. A new variable created like map from GEE map, called a map with a base map like satellite. Then map dot center object ROI. For example, here we want to have a zoom size, for example 5. Map dot add layer. The center object focuses on the region of interest or ROI, and the add layer shows or plotted over the base map. Map.add layer ROI, leave the visualization empty, and the name is ROI. Let's run. Code is running, focused on Iran location, and now you can see the polygon extracted from the United Nations geospatial data. As we want to use this data to clip the rest of the data or rest of the satellite data will be available in the next step or in the further step, I need to convert it into a geometry structure, no longer need as a feature collection. This is a very important thing because we want to filter spatially the data based on the region defined by this polygon. So in the next step, we need to bring the precipitation data. There are various precipitation data sets in the Google Earth engine, but one of them is the Persian model, one of the actually accurate precipitation models available on the net, and a combination of satellite and in situ information is a Persian dataset offering daily precipitation data from 1980s to present. So its image collection ID available here, PR dataset. Make a tuple, print the dataset collection ID, and then filter date based on a period of time. For example, I'm gonna do the spatio-temporal analysis for 10 years, from 2001, for example, to 2010, just like this. And remember to clip your data based on a region of interest, because we want to actually focus or limit our analysis to the boundaries of Iran. So make a loop function through the map, call a function lambda. Each image is going to clip based on a ROI, and then copy properties img.property names, meaning that I want to keep the properties of input data after clipping occurred. So let's run. The precipitation data is called, but they have image collection structure. Let's run a precipitation to get more detail about this product in this step. So it's about 4,000 precipitation data with daily frequency available through this data set. So that's why computation is a little bit long, and as you can see, over 3,000 satellite data called for this period of time. And when you open the collection, you can see the data characteristic, properties, band, and features. And inside the features, we will have the precipitation bands from one date to another date. So as you can see, I have a delay, a little bit delayed on my system, but here you can actually see and get information about the data structure and image collection format here. So as you can see, we have precipitation and some properties. Now in the next step, I'm gonna show you what we want to do with this data and why. So in the next step, we want to convert the image collection data structure into Xarray format using XEE dataset. So make a new variable ds sets to from Xarray open dataset. Now Xarray and XEE both combining together in this function. The input data collection is the PR. The engine should be Earth engine. Coordinate system EPSG 4326, a unique ID that's showing that's utilized for WGS84. So the region of interest defined by the geometry sets to the ROI, and the scale refers to the pixel size. If you go to the data characteristic here, you can see the pixel size is 27,000 meter or 27 kilometer. In the WGS84, the scale is based on a degree. 1 equals to 100 kilometer, 0.1 10 kilometer, 0.27 27 kilometer. So that's how it works. Everything settled and run the cell. Now we are converting an image collection structure into an Xarray structure. Make a new code. This is the DS. So we have a data set, multi-dimensional structure. Image collection is no longer valid, and now we are going out from the Earth engine. From now on, using Xarray format, we can apply the machine learning and Python algorithm on the satellite data that expand our abilities to get information from this kind of data. In the multidimensional structure, we have different dimensions: time dimension and a spatial dimension, or temporal and a spatial dimensions. And also we have a variable alongside the 3 dimension. For each location, we have a precipitation value in each time. So let's make a preview about the average precipitation over Persian Plateau. So now I'm gonna make an average array. dsmin sets to get the data set and calculate the average over temporal dimension. Let's run. There is more than 3000 arrays in this dataset and definitely takes a little bit longer for the computations. You must be a little patient, and after processing done, you can print and plot the average precipitation in each pixels. If you faced with any challenge in this tutorial, highly suggesting you to find the code example below this video in the description box, and feel free to share your ideas and ask your questions on my YouTube channel through the comment section. The process is done after 36 seconds. So the DS average is still including precipitation variable, but this is the average precipitation. Make a plot. X-axis sets to longitude dimension. Y-axis sets to latitude dimension. And the robust sets to true because we have only one image, so the time no longer needed, and the robust allowing us to skip the outlier impact on the output. This is the average daily precipitation values through the time that is less than 2 millimeters per day. As you can see, it is the daily precipitation, and the precipitation unit is the daily. You can see the lighter areas receiving more precipitation per day, and the darker areas vice versa. So, but this is a dominant precipitation pattern over the Persian Plateau. Now I'm gonna show you how to find the different patterns, different precipitation patterns through the time that is not well reflected in the one single average image. So to do this, the PCA analysis allowing us to actually find the precipitation pattern or a spatio-temporal pattern through the time. So as you can see, if you search on the net, there is a library XEOFS. This library is very suitable to apply PCA analysis without any challenge, and highly suitable and matched with the Xarray data structure. So now make a new cell, and there we need to install XEOF first and import it into the code. Pip install XEOFS, import XEOFS as XF, for example. Let's run. After the few seconds, you can see installation is completed, and you can see this message: successfully installed. Clear the output and define the PCA model. So the PCA sets to from XF go to the single and call the EOF. So the number of dimensions for the output is really important. Here you can see there is a code example. So n modes. As you can see, we have a data set including over 3000 precipitation values per pixel. So the PCA is a kind of analysis that allowing us to summarize, for example, multi-temporal data in 2, 3, 4, 5, or even 10 images. So instead of looking and checking images one by one, that is really difficult to see what's happening in the 3000 data. But here the XEF or EOF analysis, or the PCA here, is a kind of analysis that allowing us to summarize the general pattern and dominant pattern through the 10 years available in the thousands of data. Instead of checking thousands data one by one, you can see the whole of the things or the dominant precipitation patterns using 2 or 3 images. And this is really easy to justify and explain what's going on in the region of interest. So the number of the modes is default and up to you. For example, you can have 10 outputs, you can have 5 outputs, but you need to know how to interpret the results. So let me do it for 10 components. I'm gonna actually summarize all information into 10 components. So, and the next one, the PCA should be fit on the data set, and we need to define the dimension. The dim should be the time here. So, and let's run. The PCA analysis is applying on the data set. Okay, the process is done. Now, the PCA, including the components, we will have 10 components now. As you can see, we have 10 modes or 10 components. Each component showing a different information that I will show you what kind of information offering by each component. It is really to understand how to interpret the final result. So the component sets to comp or assigned to comp. So now make a plot. Component precipitations, plot them. X-axis sets to the longitude, y-axis latitude dimension, robust sets to true, call sets to mode, because the mode is the attribute or the coordinate that's showing the that expressing the image differences. Call wrap, I want to have 5 images per row. So now, as you can see here, we have multi plots that's showing different kind of information. So first of all, we have a range of value in all images. What does it mean? The range of the values ranging from positive to negative. The positive values meaning that which areas are receiving more precipitation compared to the blue regions. For example, the red areas with positive values are receiving more precipitation through the time, and bluish areas with negative values receiving less precipitation through the time. So that's the main thing before further analysis. We have different modes here, from the earliest to the latest. So the first mode actually shows the general and dominant precipitation pattern over the plateau. It's highly correlated with the average image, but the main information will be summarized in the next modes from mode 2 to 10. So, for example, you can see some of the areas like the western areas, southwestern, and sometimes northwest here, as you can see, highlighted by the red color, meaning that these areas, in addition to the dominant pattern, there are the other areas that typically receiving high precipitation through the time that you can see highlighted here. As you can see in the central part of plateau, or the Iran central area, you can see we have very low precipitation through the time. That's because this area is covered by the desert and it is very dry region. So that's why you can see we have lower precipitation through the time, but higher precipitation in the northern side and western side. And also, as much as mode increases, um, the actually the dominancy, or the, how to say, I can say, the rate of the precipitation also decreases. For example, here you can see here, for example, in the mode number 10 shows some pattern with more details, but actually uh, that means that such kind of anomalies less happening compared to the mode number 3. The lower modes showing more stronger information. The over 90% of precipitation pattern is explaining by the first four modes, and then the less than 10% of precipitation pattern is explaining by the rest of the mode. You can get more information about the PCA in this regard, but this is very interesting things. For example, I know in addition to the dominant pattern, there are some of the areas that are receiving more precipitation through the time, and we can actually get more attention to them. So, for example, in the southeast of Iran, these areas, for example, you can see the average precipitation is very low, but sometimes in some of the modes you can see it is highlighted, meaning that although the average of precipitation in this area is low, but this area is still receiving significant precipitation through the time. So, and that gives us a good information, and now we can actually have power of interpretation through the time, not only judge about the locations based on one single image. So you saw that how actually we can explain or we can understand about the spatio-temporal pattern offering by the PCA analysis. I'm highly suggesting you to apply this technique for your own region of interest and compare the estimation with your own knowledge, and then you will receive fantastic results about capabilities and applicability of these machine learning methods for climatological data analysis. I hope you like it as much as I do. Thank you for your attention.